So for RSA basics, Bob would like to receive messages from Alice via RSA. He chooses two primes p equals 7, q equals 11. What is n? So this is mostly a rule-based problem. So this first part right here. So n is actually just p times q, which is, in this case, it's 7 times 11, which is 77, right? That'll be our answer there. And the other thing is, he chooses his public key, which is E, to be 7. To what number does E have to be relatively prime to? Um, so the other number that's really important besides n, which is p times q, is p minus 1 times q minus 1, right? Because when we do E, which is the public key, multiplied by the private key, we want that to be 1 mod whatever this is here, right? And p minus 1 is 7 minus 1, which is 6, right? And then multiplied by 11 minus 1, which is q minus 1, and that becomes 6 times 10, which is 60. So this is the number that E has to be relatively prime to. And our hope is that when we multiply E times D, we have to get 1 mod 60, right? And if we kind of rearrange this, another way of interpreting this modular arithmetic statement is that ED minus 1, right? If I just subtract the two, their difference is a multiple of 60, is a multiple 60 times some k. It's a multiple of 60, right? And I can kind of, I'll bring the 60k to the other side. So I'll bring the 60k to the other side. I'll bring the 1 to the other side, and I'll replace the e with a 7, right? So this becomes 7d, right, minus 60k is equal to 1, right? So now we have to think back, like, what does the Euclidean algorithm tell us? The Euclidean algorithm tells us that if the GCD of, let's say, A and B is equal to D, right? We can write A times some number plus B times another number is equal to D. That's what it guarantees us. It guarantees that if the GCD of two numbers is D, then something times the first number plus something times the second number is going to be equal to D. We can find integers like that, integers x and y, such that this holds true. Now, given that 7 and 60 are relatively prime, their GCD is 1. So I'm gonna basically say, like, what are A and B over here? What am I trying to say here? I'm trying to say that A is equal to 7, and B is equal to 60. And their GCD um, is equal to 1. And that guarantees that I can write 7x plus 60y equals 1, right? Based on what the Euclidean algorithm tells me. Now, I can basically, once I use the Euclidean algorithm to find x and y, this x directly maps over to this d that I want over here. And this y directly maps to, I guess, a negative k, right, over here. So there's like a one-to-one mapping here, right? And if we do the Euclidean algorithm, we end up finding that the number d here is, I believe, 43. 43. So d is 43. And uh, okay, yeah. So now we have our public key, which is 7, our private key, which is 43. And so 43 times 7 should give us, and you can verify this on your own, will give us 1 mod 60. It'll be 1 greater than a multiple of 60. And now for part D, imagine Alice wants to send, wants to send Bob a message, x equals 30. She applies her encryption function. To 30, and what is the encrypted message? So this is, a very straightforward application of the definitions, right? So you start with, basically, whenever you're encrypting a message, right? All we're doing to that message is we're raising it to the power of E, and sending whatever the remainder is when we divide that by n, right? So x to the power of e mod n. So specifically, we're doing 30 to the power of 7, right? But the x is 30, the message we're trying to send. E is our public key, and n is the mod, which is 77, as we calculated in the beginning. And then this thing ends up being, if after some calculation, ends up being 2. Okay. So 2 is the thing that we are actually sending to Bob, right? And then Bob over here, he's like, okay, he takes anything that he gets, right? This is like that X prime. That's like the encoded message, right? Any encoded message he gets, he's going to decrypt it by doing the following. He'll take that message that he got and he'll raise that to the power of D, which is his private key. And then we'll just take that mod n, right? So specifically, if we have 2 over here, right? That's x prime. That's what we found in the previous problem, right? And then raise it to the power of d. D is 43. 2 to the power of 43 mod 77. If you calculate this out, what is the remainder of 2 to the power of 43 modulo 7? We will get, we should get back what we started with, right? Which is 30, right? Thank you.